characteristics of wave motion. Now, to be able to understand this, we are going to consider an oscillatory motion. By one, we can consider a mass which is vibrating on a spring, moving up, down, up, down. If you attach a mass on a spiral spring and then you displace it vertically a bit, it's going to display a certain motion that we are going to see. Also, we are going to consider the oscillation of a pendulum bob, or when we swing a pendulum bomb, the movement that it's going to portray. So with this, we can say that we are going to explain with reference to an oscillatory motion of a mass attached to a spring or a swinging pendulum bomb. So explained. Explained with reference to the motion of a mass attached to a spring or a swinging pendulum bomb. A swinging pendulum bomb. So in this, we can start with the first one, where we are talking of a mass that is attached to a spring. I'm sure you have learnt about a mass. You know what is a mass. In the previous topic, Hooke's law, you learnt about these masses. Then when it is attached on a spring, when you are defining or verifying the Hooke's law. So here we are going to consider, this is our fixed point, and then here we have a spring. That's our spring. On this end we have a mass attached onto it. So this is our mass. So that's what we have. This is our, we can call this one A. So this is our spring, and here we have the mass. So in this, if we consider this to be our mean position for the mass, this as our mean position at the center of this mass. So if we call this, we can use letters. For example, we can talk of A. So when it is given some vertical displacement, it will swing in this manner. It moves from here up, back again here, again. That's how it will be swinging up, down, up, down. So if we have our A here, so this is how it swings from the mean position up, then down, then. So we have it this way. So if we have this as our, so if we have it this way, so if we have this as our A, then we can have this upper part. If it is moving from A up, then through A, then down, then A, we are going to have it this way. So if this is our A, then this we can call it B, and then here we have C. So how will the mass be moving? The mass will have an oscillatory motion described as follows. So it is going to move it from A here. It will move from A, then it moves to B, then back to A, then moves to C, then it moves to A, then it moves again to B, then it moves to A to C, and the motion will continue. So that is what we are going to have for our motion. But now we want to know, when do we say a complete oscillation is attained? So if it moves from point A, moves to B, through A again, back to C, and then to A, then we'll say that that is a complete oscillation. So we can say for a complete oscillation, we are going to have the following. So if we are taking it from A, we can take it from anywhere, because if we start from B, if it moves from B, they'll move back to A, to C, to A, then to B again. But if we start from A, For a complete oscillation, we'll say a complete oscillation has been achieved when it moves on both sides and then comes back to its initial position. So if it is oscillating in this manner, it's moving up, then through the mean position down, then back to the mean position, then that is a complete oscillation. So if it is from A, it is going to be A, then B, then back to A, then to C, and then back to A. So that is a complete oscillation. Or if we are starting from B, if it is from B, it can also be B, then it moves to A, then to C, then back to A, and finally to B. That's a complete oscillation. Or, so we can either talk of this or that, or if we are starting from C, it means that it will move from C to A, then to B, then back to A, and then again to C. That is the starting point. So that is a complete oscillation. Hope you get that. So for a mass attached to a spring, you can see, for us to say that it has moved one oscillation, then it has to go back to its initial position through the two signs. So if it is from A, it has to move to B, then back to A, to C now on the other side, and then back to the starting point. That is now for a mass attached to a spring. Now we want to consider a swinging pendulum bump. A swinging pendulum bump, and see how we can tell that it has completed an oscillation. So in this one, we again consider a fixed point. In this, we are going to use a string to attach. We attach our pendulum bump here. So this is our bump here. This is the pendulum bump. That is the initial position. So if we give it a slight displacement horizontally, so we give it a displacement, it's going to swing this way. So it is going to swing to this direction. We can use a dotted line. So it is going to swing to that side, and again it will swing to on the other side. So we have it that way. So this is our pendulum bump. Pendulum bob. So this is what we are talking about. If here we have our pendulum bump. So this is our mean position. We give it a slight displacement. This is our fixed point. We are going to have it move this way. So you can see how it is moving. So if we have our fixed point again at this point, we give it some slight displacement. You can see how it moves. So that is the swinging of a pendulum bob. So it is going to swing. Let's say we have our point A here. We can call this B and this one C. Or to make the contrast, let's use other letters than the one that we have used for the mass. We can use X, Y, Z. X, Y, and Z. So for us to say that it has completed one oscillation. So for one complete oscillation, before we move to one complete oscillation, this is how the pendulum bob will move. So it's going to move from, let's say it's starting from Y. So we have from Y to X, then back to Y, then to Z, to Y, to X, to Y, to Z, from Z to Y, from Y to X, and so on and so forth. So that's how the movement is going to be. So for one complete oscillation, we are going to have the following. So if we are from Y, it's moving from Y, we'll move to X, then through Y to Z, and then back to Y. So that is a complete oscillation. So if we have our pendulum pump here, moving to this side, back, then this other side, then the starting position, then that is for a complete oscillation. Then if we are starting from X, because we can start from any point, if it is from X, moving to Y, then to Z, then through Y again, and back to X. That is another complete oscillation. Or we can have, if we are starting from Z, it's going to move from Z to Y, then from Y to X, from X to Y, and finally back to Z. So we'll say that that is a complete oscillation. So that is on complete oscillation with reference to the motion of a mass attached to a spring or a swinging pendulum pump.